Okay, we're recording here, and I'm gonna bring up this screen. I hope I am. Come on, there it is. Good. And what else do I want to do here? I'm gonna turn my video on here. Okay, good. So, serendipity. That's where I'm starting. Is with serendipity, and that's an amazing thing. So pre-COVID, Pierre Ramon suggested to try to calculate the PMNS and CKM matrices, the neutrino and quark mixing matrices using the impedance model. And so naturally that went to the top of my physics to-do list. And here some years later, I was quite surprised. I was trying to calculate PMNS for the muon collider. There's a whole discussion that goes on about that, how to use these topological impedance matching to stabilize, to extend the lifetime of the muon, and massless neutrinos play into that. So this was from 2020 and 2022. Back in 2012, Richard Tallman, we're walking to lunch from physics to the cafeteria, and it was like 3 minutes it took. He's very quick. 3 minutes it took for him to understand a lot of the consequences of the model we were talking about. At which point he said, "This is going to be the hard part, getting you guys to think in terms of impedances," and that's certainly proved true. So coming back to this just briefly, so what we're doing is we're doing a precise direct calculation of the quark mixing matrix. It's very short, very simple. If we go to this view here, actually, I'll walk you through the whole thing. Come on, slide sorter, give me this. Okay, and let me put this into presentation mode. Nope, it wants to go to the individual slides. Okay, so we start here with the CKM matrix and show its unitarity and the variance. It's accurate at the 1% level. The variance here, and the biggest variances. I should go back and do this. The biggest variances here is in the Cabebo angle. It's the worst fit of all nine. The Cabebo angle is the angle whose tangent is the ratio of these two terms here, the 2249 and the 9735. That's the standard model, and the impedance model gives us this. So it's off by a degree. But then if you look at this is where the biggest variances are here, these two terms. And so it actually gets a little bit better than this. It might be better than 1% if this fit was better, and everything else is compensating for that. So this is curious what these two modes are, why they're not. So anyhow, we've got a nice model here that's incredibly precise. I'm just so amazed by how these pieces fit together. This is what you saw on the first slide up here, and this is all you need to make the calculation. Just these scale invariant impedances, because what we're interested in is the phases in quantum mechanics. It's the phase coherence that defines the boundary of the wave function. So with just the impedance of free space here, the photon far field, 377 ohms, this, in the standard model, and the theorists forgot about it. They set this to 1, dimensionless unity, along with Planck's constant and speed of light and everything else, and then forgot about the rest of them as well, all of these topological far field impedances. The one slide, the next slide here, I'm just going to go ahead and hop over there. Come on, here. So here again, what we call Z0, here's the photon impedance at 377 ohms, and up here's quantum Hall, scale invariant impedance. This is scale invariant, and presumably you can have a scale invariant impedance here as well, although it's not totally clear to me that is true. And that has some potential interesting consequences, but bypassing that for now, what we're looking at here, this plot here is from Malcolm McGregor. Oh geez, I hope I have him referenced here. I'm sorry, Malcolm. Oh yeah, here he is. The Power of Alpha by Malcolm. He his career was spent basically, and there's a lot of good insights in terms of the quark structure, in terms of the Standard Model, and how he relates the unstable particle lifetimes and masses to the fine structure constant. So anyhow, this is the unstable particle lifetimes. Or in lengths, it's the lifetimes times the speed of light, which is the coherence length. It's the quantum boundary. So you got the neutron out here, and alternating fermions and bosons, the muon here, and then the kaons. And again, we alternate fermions and bosons going back. But these things here, these four impedances, that's all we need to get this calculation here, which is you can do for yourself. You know, it's simple enough. And this is what we're comparing it to. If we go back to here to the data in the model, then the data here is the model is the italics, and so what we're comparing it to is the 2022 data group. So that's pretty much it. You know, a person could go on and talk about this for a while. I think the most interesting part is it appears that we're ignoring the parity violating, the CP violating phase, because we don't need it to do the calculation. All we're using is just the impedances. But the thing is that CP violating phase is already present in the model. It has the topology built into the mass gap wave function, into the math. Or maybe, no, it's not into the math. It comes in from QED. So anyhow, that's I think pretty much all I want to say for the moment. If you go on and look at this, I'm not gonna discuss any of this in detail. This shows how to calculate this thing here, the quantum impedance network of the mass gap. That's the electron Compton wavelength we're looking at here, and a few of the different modes. There's many more modes than shown here. We've got 16, I think, is all you can plot in MathCAD, and there's 64 times 8 actual if you go to three body interactions. Yeah, I just had a phone call. I'm going to turn this on. Turn off if you will. Thank you. So then just to briefly go through what's left of this. So that shows how to do the calculation step by step, and then this shows gives a historical perspective on the model and how we got to where we are. And I think I'm going to end this here. How do I stop this? I'm looking, but I'm not seeing it yet. Share. That's funny. I would have expected it to work from where I started. The tools, where are the tools here? Foo. What do I got to do to get back to where I want to be? Pause. I'll go for pause for now.